All right, we are back. Chapter 11, acids and bases. Probably our last full chapter that will show up on the final. But we'll see. Acids are found in lots of common foods. For example, citric acid you might find in lemons and limes, citrus fruit. Acetic acid is the active ingredient in vinegar. Tartaric acid is commonly used to coat sour candies. Think of the first they're sour, then they're sweet sort of candies. Acids combine with saliva in your mouth and they produce H plus ions. Those H plus ions react with protein molecules in your tongue. They send electrical signals or nerve impulses to your brains that you experience as a sour taste. What is an H plus ion? What's in an H plus ion? It's hydrogen. Hydrogen has one proton, one electron. If you take the electron away, H plus is a proton. Protons are sour. There's your fun fact for the day. Protons are sour and electrons are blue. Unrelated. Here's some of the properties of acids. Acids tend to have a sour taste. That's good to know. Acids also dissolve many metals. Also good to know. And it will turn blue litmus paper red if you have blue litmus paper. We sometimes use blue and red litmus paper because they're cheaper, I think, than the multicolored litmus paper. So here's an example of some zinc metal dissolving in hydrochloric acid. It produces hydrogen gas, which is explosive. Some acids are listed here. So here's some of our chemical names: hydrochloric acid, sulfuric acid, nitric acid. These are ones that we've seen before. Some of these show up in household cleaning products. Others are used in agricultural applications. For example, sulfuric acid, commonly added to drip lines for irrigation and used to acidify soil for blueberry fields. On the other hand, we have bases. Bases have a bitter taste, and they have a slippery feel. If you get base on your hands, it'll make your hands feel slippery. And they do the opposite of acids for litmus paper. They turn red litmus paper blue, so it's the other direction. The bitter taste arguably the more important than the litmus paper colors. There are several consumer products that contain bases. Things like Drano that you maybe have used to try to clear out the pipes in your house. And things like tonic water that has quinine in it. Yeah, quinine in it. Bases feel slippery because they react with oils on your skin to form soap-like substances. So when you get base on your hands and it makes soap from your hands, that's hand soap. Gross, but cool. Bases are commonly used, have historically been used, and I think are still used for the production of soap. Just usually not involving hands until the final product. Bases are a little bit less common in foods. Alkaloids are a class of organic bases, so they're carbon-based bases found in plants that are often poisonous, and that bitter taste warns us against eating them. That bitter taste also showing up in things like Indian Pale Ales and other sort of adult beverages. And coffee also has some bases in it, like caffeine, that might impart a bitter flavor. You can also get bitter flavors if your coffee's burnt. So that bitter flavor is a warning, and I'm assuming that you would also experience that bitter taste if you were to eat or taste something like sodium hydroxide or potassium hydroxide, magnesium hydroxide. Maybe seeing a trend here with these hydroxides, calcium hydroxide. And then another one that's not a hydroxide is ammonia. We'll talk about some of these bases more later. But first, we want to start out with a definition for bases. And so we are going to start off with our Arrhenius definition of bases. This is our Arrhenius definition for acids. Our definition is that they produce H plus ions in aqueous solution. So if you add a compound to water to make an aqueous solution, and it produces H plus ions directly, then that makes it an Arrhenius acid. I'm emphasizing that this is an Arrhenius acid because there's other definitions of acids and bases, one of which we will learn and several of which we will not learn. HCl, hydrochloric acid if it's dissolved in water, is a covalent compound. Just by itself, HCl doesn't have any ions in it. If you add it into water, water goes crazy, rips it apart, and now you've got H plus ions and chloride ions. That makes it an Arrhenius acid. Even though HCl by itself, if it's not aqueous, would be a molecule. So you take HCl, you add it into water, which is this shade of blue for some reason, you get H plus, you get Cl minus, dispersed throughout. We're omitting something with this representation. Who knows what we're omitting? Any ideas? Sort of omitting. The water. It's just drawn in as blue, but there's little bits of water around all of these H pluses and Cl minuses. Positive or negative sides, depending. We're also simplifying things with that diagram. So H plus ions, protons, are highly reactive, and if you're in aqueous solution as a proton, you are always going to be bound up to water molecules. You're never going to find H plus ions alone. They're always going to be reacting with water molecules, H2O. And so they're actually going to be in solution as this compound, this H3O plus. H3O plus we're using interchangeably with H plus. We'll often use H plus just because it's shorter, but when we're talking about H plus, we're actually meaning H3O plus, and H3O plus is the hydronium ion. I believe that is on our list of ions to know. And again, in water, these protons, these hydrogen ions, will always have an H2O that they are paired up with. We'll typically be using them interchangeably. So if you see one, you should know that we're talking about potentially the other. Okay, when we are writing bases, acids, when we're writing the molecular formula for acids, the ionizable hydrogen, sometimes multiple, go first. For example, the formula for formic acid's an acid because it's got acid in the name, is written as H in the front, CHO2. Other times it might be CH2O2. In this class, we're generally going to show the ionizable protons first. It's also a helpful indicator that something is an acid. I believe we talked about that in nomenclature way back when. So that's our equation, our formula. The structural formula would show how the atoms are bonded together. So this HCHO2, we can also show it like it is here on the right, where the carbon is bonded to a hydrogen. There's also a hydrogen bonded to the oxygen, and it's the hydrogen bonded to the oxygen that comes off in water, or can come off in water, which is not relatively not important for this class. Our Arrhenius definition for bases, let's do that in a brighter color. For bases, they produce OH minus ions, hydroxide ions, also in aqueous solution. So Arrhenius is aqueous. If you see Arrhenius, you should think aqueous. You should think H plus, you should think OH minus. H plus for acids, OH minus for bases. So sodium hydroxide, an ionic compound, is an Arrhenius base because it dissociates into Na plus and OH minus ions in solution. So when you add it into water, when you add sodium hydroxide, usually as pellets, to water, it dissociates into sodium ions and hydroxide ions. These will also have waters all around them, helping to stabilize. OH does not always mean that something is going to dissociate or act as a base. For example, CH3OH is methanol, wood grain alcohol, and does not dissociate in solution, so it's not a base. That's a molecular compound. Sodium hydroxide, being ionic, will dissolve in water. So not everything that has OH in it is a base. Under our Arrhenius definition, acids and bases naturally combine to form water. So we get this net ionic equation for acid-base reactions. We've got the H+. This is acid reacting with the OH-, the base, to form water, which works for some acids and some bases, but it doesn't work for all of them. So some substances will act as bases even though they don't have OH- in them. And that's a limitation of the Arrhenius definition. Another limitation is that it doesn't apply to non-aqueous solvents. So if you're in something other than water, Arrhenius doesn't apply or doesn't work. And so we have the Bronsted-Lowry definition. The Bronsted-Lowry definition for acids and bases are more general. So an acid is a proton donor, and a base is a proton acceptor. Proton donor mean it's giving hydrogen. H+. Giving away H+. This definition, the Bronsted-Lowry definition, is nice because it applies to a wider range of things that behave like acid-base reactions. It's focused on the transfer of protons rather than focusing on do they produce protons or hydroxides in solution, aqueous solution. HCl also counts as a Bronsted-Lowry acid because in solution, this time we're looking at aqueous solution again, it donates a proton to water. So this H gets sent over to the H2O, and that's where our hydronium comes from, and then we're left with the chloride ion. And so because HCl can donate this proton to water, it acts as a Bronsted-Lowry acid. It also works for things that are bases like ammonia, NH3. NH3 doesn't contain OH- ions, but it still produces hydroxide ions in solution. And the way that that happens is that it actually steals or accepts a proton from water. And so the H2O, which is H bonded to OH, one of these goes to the NH3 to make it NH4 plus ammonium, and then the rest of it is left as hydroxide. So it still produces hydroxide in solution, it just doesn't separate out into hydroxide in solution. Questions about our definitions so far? All right, we're cruising. So part of the proton donating, proton accepting is that both of those things happen at the same time. They always occur together. Acids, which are proton donors, and bases, which are proton acceptors, always occur together. This is sort of like if you're doing a little bit of house cleaning, maybe because you just bought a bunch of stuff for Black Friday, Cyber Monday. If you're getting rid of stuff and you're going to donate things and you tell your friend, hey, I'm going to donate all these clothes, you want to come with me? And they say, hey, where are you going? And you say, what do you mean? I'm not going anywhere, I'm just donating them. They'd say, what do you mean? Where are you going? Where are you donating them? Who are you giving them to? And if you said, what do you mean? I'm just donating them. I'm not giving them away anywhere, I'm just donating. Like, they would look at you like you're crazy because you have to give them somewhere. And the same thing applies to protons. Someone is donating the proton, someone is accepting the proton. if something is being given, it has to be being received somewhere, even if that somewhere is just you're donating it to the trash can because it's no longer suitable for human use. Or animals, I guess, because animals could also use some of the things you donate. So these are the two examples that we looked at before. And if you notice, in our first example, water is accepting the proton from our acid. And then the other example is giving proton. It's acting as the acid. So water can do both, and so we call it amphoteric. So our definition here, amphoteric, a substance like water that can act as an acid or a base. It can do both. It's the switch hitter of acids and bases. It doesn't do both, but it can do both. It does one at a time, depending on the circumstances. We can also, with our equations, flip them and make them go in reverse, especially for things like ammonia, which has a reversible proton donation. If we flip the left and the right side, so what was our products is now our reactants, right? We get our ammonium on the left side with our hydroxide, and our ammonium can give that one of those protons back to the OH minus to reform our ammonia and our water. The double-headed arrow meaning that it goes both ways. And so because it can go both ways, this NH3 and NH4 plus are often referred to as a conjugate acid-base pair. These are related to each other by the transfer of a proton. So one has an extra H plus compared to the other one. A conjugate acid-base pair has one acid and one base in it. So in this case, for ammonium and ammonia, the ammonium, the NH4 plus, is the acid. The NH3 is the base. The NH4 plus can give a proton. The NH3 can accept a proton, and in doing so, they switch to the other form. Here it is again, conjugate acid-base pair. Shows up twice, it might be important. All right, here's more. Shows up 3 times, it might be important. So a base can accept a proton and become a conjugate acid. An acid can donate a proton and become a conjugate base. So what we were looking at before was our ammonia, which is a base because it can accept a proton. It can accept a proton, and in doing so, it becomes NH4 plus. NH3 is a base, NH4 plus is an acid, and it's the conjugate. It's the counterpart to the base. It's a little bit of assistant regional manager versus assistant to the regional manager. One of them's correct. In every conjugate acid-base pair, you've got either a conjugate acid and a base, or an acid and a conjugate base. Each of the 3 words shows up 1 time. Do we have any questions about our conjugate acid-base pairs? So if you have an acid on the left side, it can turn into a conjugate base on the right side. It doesn't always, but it can. If you have a base on the left side, it can turn into a conjugate acid on the right side.
Can it be two conjugates?
There cannot be, so there can be two conjugates, right, because we're seeing a conjugate base and a conjugate acid, but we've got two pairs. We've got the red pair, we've got the blue pair. So there can be two, but they're going to be separate pairs. Conjugate is usually on the right side. If we flipped it, then the conjugates would now be the acids and the bases, and the non-conjugates would be the conjugates. So it's all relative. All right, let's look at some examples, real-world examples. In each of these reactions, let's identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. I'll give you a little bit of time to work on it. Okay, let's start with our acid and base. In A, which of these two is our acid?
Water.
It's not water. It's the other thing, acetic acid, because it's got H in the front. The reason it's not water in this case is because we have a better acid. Water can do both. It doesn't particularly like doing either, though. So HC2H3O2 is our acid, and we can tell that it's our acid as well because we've got C2H3O2 minus on the right side. It's gotten rid of that H that was in front. And water picked it up. So what's happening is our acetic acid is giving proton to the H2O, and it's becoming H3O+. Since H2O is receiving the proton, it's accepting the proton, it's the base. And then in B, let's look at what happens. We've got CH3NH2, we've got H2O. On the right side, how have they changed? One of them got an extra proton, one of them lost a proton. Which one gave their proton away? Water. So water, H2O, in this case, is the acid because we created this OH minus from the H2O. So because it gave away the proton, that makes it the acid. The CH3NH2, methylamine, I think, is our base because it accepted the H+. Questions about acids, bases? Great. Conjugate acid, conjugate base. Our HC2H3O2 is an acid. What pairs with an acid? Conjugate acid or conjugate base?
Conjugate base.
Conjugate base pairs with acid because that's the other two words that show up in the phrase conjugate acid base. So we're looking for conjugate to the acid, which is the conjugate base. Which one of these two things on the product side looks most like HC2H3O2? Is it the left one or is it the right one? It's the right one. So that's the conjugate base. So our acid pairs with the conjugate base. And that makes H3O plus our conjugate acid. It's a conjugate of something, and it's an acid. Conjugate acid, not conjugate to the acid. Hopefully it's not too confusing. In B, we've got our base, we've got our acid. Let's look at what looks most like our base. Is it this one? Is it this one? Is it 1 or 2? It's 1. 1 looks more like it. So this is a conjugate. We could call it a conjugate. Is it an acid or a base? it is an acid. So our base pairs with a conjugate acid. Never an acid and a conjugate acid, always a base and a conjugate acid, acid and a conjugate base. And then OH minus would be our conjugate base. Sometimes, instead of using H2O here, we might have sodium hydroxide. Excuse you, no, go away. And instead, we would have H2O, and we would have NaC2H3O2. That would be aqueous. Our HC2H3O2 is still our acid. And our conjugate base is in this nacho compound. Even though it has a sodium in front, because it's aqueous, this sodium is not actually connected. It's just a counter ion to the C2H3O2. So sometimes there's another ion in front. All right, our big reaction with acids and bases, our most important one arguably, is acid-base neutralization reactions. So acid-base reactions generally form water and a salt. Not necessarily salt, sodium chloride, table salt, but just a salt being an ionic compound. Sometimes, like in this example, it is actually salt, which is a salt also. So our acid-base neutralization reactions are going to have an acid, they're going to have a base, and those react to form the H and the OH part go on to form the H2O, and then the rest of the thing also goes together. The Na plus and the Cl minus also go together. It's also sort of a double displacement reaction, because notice we're taking the blue parts and we're pairing them up, we're taking the red parts and we're pairing them up. So in that way it's also a double replacement reaction or double displacement reaction. That's arguably our biggest, most important acid-base reaction. Questions so far? All right, the train keeps running. Some neutralization reactions, like the reactions of acids with carbonates or bicarbonates, things like washing soda or baking soda, things that have CO3 2 minus or HCO3 minus, produce water, gaseous carbon dioxide, and salt. These are also a type of gas evolution reaction. So for example, this beaker had baking soda in it, sodium bicarbonate, NaHCO3. And I added to it an acid, just vinegar, acetic acid. And it made this fun, frothy, foamy gas. This is often the backbone for the very classic paper mache volcano science fair project that is probably not as popular anymore, but used to be really popular. I did that in my backyard. I couldn't find a good image, so I was like, well, I'll just do it myself. Okay, so So we can write equations for neutralization reactions. What do neutralization reactions produce? Water. And salt, a salt, not necessarily salt. So we're looking for the molecular equation. Nice. What do we have in our molecular equation? Ions, molecules. Do we have charges? No charges. What's a different type of equation other than a molecular equation? Ionic, either complete or net ionic. So we're doing the molecular equation, we're showing the full and complete structures, not as they exist in solution, but with neutral compounds. Neutral formulas. So we've got aqueous H2CO3 plus NaOH. These are both aqueous. Which one of these, the left or the right, is our acid? Left, why? It has H in front. H in front means that it's the acid. So this is our acid. It's carbonic acid from carbonate. One of our products is going to be water. We're also going to have a salt. What's our salt going to be? One way we can figure it out, NaCO3 is correct. So we can separate to our individual ions and run it like a double replacement reaction. Our anions get swapped. We would rewrite this as H plus with the OH minus, Na plus with the CO3, 2 minus. The H plus and the OH minus go together to form H2O. It's a 1-to-1 ratio. For our Na plus and our CO3, 2 minus, the charges don't balance out, and so we get to crisscross, or swap and drop. We end up with Na2 CO3. To start with. At least. If we wanted to do the neutralization reaction part, this is CO3 minus, CO3 2 minus that we have in here, and so this would also produce carbon dioxide if we actually did it. I'm going to skip that because I don't like gas evolution reactions. That's the whole reason. You should know about them, but I don't like them, so we don't do them. Okay, and then to balance it, because we would be balancing this normally. To balance it, we would have to put a 2 in front of our NaOH and a 2 in front of our H2O. Questions or confusions? Usually, for acid-base neutralization reactions, we can get the left side balanced, because that's usually what we care about. We usually don't care about the water or the salt. To get the left side balanced, we just need an equal number of H's in front and OH's from whatever our base is. So we've got 2 H's in our H2CO3. We've got 1 OH in each of our NaOH's, so we can just put a 2 in front of our NaOH, and that'll get our acid and base balanced, and that's usually all we care about. So that can be a shortcut sometimes. Acids will also react with metals. So one of our fun facts about acids was that they dissolve many metals, not all metals, hashtag not all metals, but many metals. And so if you put something like zinc or magnesium in hydrochloric acid, it will go on to produce H2, which is hydrogen gas, and this thing, which has a positive ion and a negative ion. It's an ionic compound that is also a salt. So acids dissolve metals to form H2 and a salt. It's also a double displacement reaction. Some metals don't readily react with acids. Usually that's precious metals, gold, silver, iridium. I don't think tungsten's particularly reactive either. Platinum, palladium, rhodium. Expensive metals generally don't dissolve in regular acid. So our reaction, here it is written out with more words. We've got a dissolved salt and hydrogen gas that gets produced. We won't really get into the bones, the nuts, the details of why they do that. You can also have them react with metal oxides. So there's metals, there's also metal oxides. Any guesses on what's in a metal oxide? Yeah, we're adding oxygen to a metal. So acids react with metal oxides. Oxides meaning that we've got oxygen on there. And it produces water and a dissolved salt. So notice, if we had just the metal, I'm going to fake cover up things on the board. Right? If we had just the metal, then we would make H2 gas. We're adding oxygen. We're also adding oxygen to the H2, and so now it's H2O instead of H2. So I think that's fun. So it's water instead of H2 gas, because we added an oxygen to it. All right, some equation writing for you to practice. Please write an equation for each of these reactions. Hydroiodic acid with calcium metal and hydrochloric acid with magnesium oxide. Okay, if we were stuck with nomenclature, here's our reactants. Hydroiodic acid, hydro meaning it's binary, so it's just Hi, and calcium metal is Ca. In B, hydrochloric acid is HCl, again a binary acid, this time reacting with magnesium oxide, magnesium being Mg, oxide being O. The ions that those would normally form, magnesium would generally form a 2+, oxygen would form a 2- because of the columns that they're in. If you're confused about the columns that they're in relating to their charge, Logan would be more than happy to talk to you about that during his SI session. Because the charges are the same, we just combine them, MgO. And now you can come up with the products. Okay, so our products for a metal like calcium dissolving an acid, one of our products is going to be hydrogen gas. The other is going to be a salt. So everything that's not hydrogen gets added together. So our calcium and our iodide are going together. Calcium is going to be 2+. Iodine, when it forms an ion, iodide, is a 1-, again because of the columns that they're in. And so it's Cai2. And then if we wanted to balance it, we just add a 2 in front of the hydroiodic acid to balance out the H2 and the I2. When we're doing an oxide, it's the same idea for the products, but we've added oxygen to the H2. So our H and our O go together. We've got H2O, water. And then the other things add together, and so we'll end up with MgCl2, again because magnesium is a 2+, and chlorine forms a 1- chloride. So they go together in a 2-to-1 ratio, similar to the calcium and iodide in the previous problem. And to balance this one, we also add a 2 in front of our HCl. You won't always add a 2 in front of the acid, but in this case we are. Questions? Okay, base reactions. The most important reaction for bases is neutralization reactions, which we already talked about. And we're going to mention another one. The other kind of base reaction that we'll cover, we're just talking about it, is sodium hydroxide reacting or other hydroxides reacting with aluminum and water. So aluminum is a weird metal. It's one of the few metals that dissolves in a base. So if you take sodium hydroxide or potassium hydroxide, you react it with aluminum and H2O, you make this fun compound. And also hydrogen gas. In our alum lab, we reacted aluminum with a base to produce this, and then we did other stuff with it later. So we're just mentioning that. If you go on to take Chem 2, you'll see that come up again when you talk about acids and bases. Or you might see it come up again. Okay, so that's our reactions. We had acid-base neutralization reactions. That's a big one, huge one. Acids dissolving metals, acids dissolving metal oxides. Those are kind of the 3 important reactions. Now we're going to talk about strong and weak acids and bases. So starting off with strong acids, hydrochloric acid HCl, hydrofluoric acid HF look similar, right? They're both binary acids. However, HCl is a strong acid. It completely ionizes in solution. HF is a weak acid, and weak acids do not completely ionize in solution. So they have different behavior when you add them into water. So strong acids ionize completely. Strong here is the same as strong when paired with electrolytes. So with our lab where I was putting the little solution and the light turned on or not, the strong ones were where it turned on. The dim one was one of our weak electrolytes. So strong acids are strong electrolytes, meaning that they ionize completely. That's weird. Strong ionizes completely. What this means is that you will not see any of the formula units intact. So if we add HCl into water, it completely separates to H plus and Cl minus. No HCl units in solution. So if you take a 1 molar, molar being our concentration unit, hydrochloric acid solution, our H3O plus concentration will be 1.0 molar. Because we put in 1 molar HCl, it's a 1-to-1 ratio between HCl and H plus is the same as H3O plus when we're in water, so it's also 1 molar. And these brackets around a chemical compound means molar concentration of X. So this brackets around our hydronium ion equals 1 molar. That's the concentration of that ion. Here are some strong acids. Some of them are bolded. Any guesses why they're bolded? That's right. Those are the ones that you should have memorized. So those are our strong acids. We've got such beautiful examples as hydrochloric acid, sulfuric acid, and nitric acid. Just 3 of them. Nice. While we're here, we're also going to talk about proticity. I don't think that's what anyone calls it, but I'm calling it that. So monoprotic acids contain 1 ionizable proton, the mono being 1 and protic being proton, 1 proton acids. They've got 1 H in front. Sulfuric acid, H2SO4, is an example of a diprotic acid. Di for 2, protic for proton, which is H+. So these contain 2 ionizable protons or hydrogens because there's 2 H's in front. The number of H's in front is the number of hydrogens that can pop off or ionize in solution. How many ionizable protons does phosphoric acid have? That's phosphoric acid. If HCl has 1, H2SO4 has 2, how many does H3PO4 have? That's right, it's 3. So that would be an example of a triprotic acid. 3 hydrogens can pop off in water or ionize in water. Weak acids, on the other hand, do not completely ionize. They are weak electrolytes. They're poor conductors of electricity. And one of the ways that you can tell that they're weak is that we have HF units in the chat, in the solution. Another way that we can tell, if we've got an equation, we've got the double-headed arrow. So it goes both ways. You will only see that for weak or reversible solutions/reactions. So since HF is a weak ion, some of the H3O plus and the fluorides are also going back to form HF. They're going both directions. For weak acids, there's a lot. And there's 2 that are important for you to memorize. Those are hydrofluoric acid and acetic acid. Hydrofluoric acid is the one that shows up in Breaking Bad that they use to dissolve a bathtub unintentionally. And acetic acid is the one that is in vinegar. It's HC2H3O2. Most carboxylic acids are weak. Carboxylic acids are like the example that we saw before with formic acid, which was this thing. You don't need to know what a carboxylic acid is for the class, but just in case you were curious what it is, it's that structure of the acid. Sulfuric acid, which is listed with our strong acids, is a diprotic acid. The first acid can put the first part, the first one, is strong. The second one is weak, which is fun, in my opinion. Okay, so knowing whether things are strong or weak can play a role in determining ion concentrations in solution. So we want to determine our H3O plus concentrations for each of these solutions. The first thing that we need to do is identify, are they strong acids or weak acids? HC2H3O2, acetic acid, is it strong or weak? It is weak. We know that because we can reference back to our chart. It's here in our weak acids table. So this is a weak acid. How about HNO3? Is that strong or weak? That one is strong. You could reference back to your strong acids table. And then how about HF? Is it strong or weak? Weak. You can thank your lucky stars that we are not doing calculations to figure out the actual concentration of ions in weak acid solutions, unless you go on to take Chem 2, in which case you will. But we're not going to do that, so we're going to talk about them as being a concentration or being less than or greater than a concentration. So we want to find the H3O plus concentration for each of these solutions. How many ionizable protons does acetic acid have? Where do we find our ionizable protons? What does ionizable mean? What does cancelable mean? Any ideas? Ionizable means it can form an ion. Ionizable, can ionize, form a charged species. So our ionizable hydrogens are the ones that can form a charged species. They can become a proton, they can pop off, they can be removed. And those are always going to be found in front. So we've got 1 in front of our HC2H3O2. So if we were to put this into solution, into some water, it's a weak acid, so it won't completely dissociate, so we draw the double-headed arrows. It will form H3O plus, which we'll often just write as H plus. Right, it'll separate out, and we will also have the negative part, the C2H3O2 minus. We've only got one ionizable proton, so at max we would have one H plus for every HC2H3O2. We've got 0.8 molar. If that were to completely ionize, 1 H plus out for every 1 HC2H3O2 in. Doing a stoichiometry here. It would be 0.80 molar H plus, if it's strong. If it completely dissociates, that's what the concentration would be. Does it completely dissociate? No, it does not completely dissociate. So it will be less than that. It's weak, so it will be less than 0.80 molar. So concentration of H plus, which is the same as H3O plus, is less than 0.80 molar. Questions about that process? For HNO3, it's a strong acid, so it completely dissociates. So if we wanted to write ourselves a little equation, it goes to H plus and NO3 minus. These are 1 to 1, and so the concentration is the same. Concentration of H plus equals 2.25 molar. Because it is strong, 1-to-1 ratio of H plus to HNO3. If it was diprotic, it would be different. If they both popped off and it was diprotic, then it would be double. If it was triprotic and they all popped off, it would be triple. That doesn't happen, though, with acids. And then for HF, it's going to be, since it's weak, it's going to be less than, again, less than 0.70 molar. Doesn't completely dissociate. We don't have the tools to talk about how much of it actually dissociates, thankfully, because that makes it a lot easier for us. There's also bases. So strong bases completely dissociate in solution. And we've got some examples. We've got, reading down the left column and then the right column after that, we've got sodium hydroxide, lithium hydroxide, potassium hydroxide, rubidium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. What do these all have in common? Hydroxide, yeah. These all have hydroxide, which is the OH minus ion. There's another thing that they all have in common. It's the type of thing that they are. What type of thing are they? Are they, let's think about our nomenclature categories. Are they acids, molecules, or ionic? They're ionic. So they're ionic. They've got a metal and a non-metal part. In this case, the non-metal parts are hydroxide. The metal part is the metal. So when you see something like this, you see that OH, you think to yourself, oh, with the secret minus there, that's a strong base. There's a little catchphrase. Oh, that's a strong base. Unlike diprotic acids, which ionize in 2 steps, bases that contain 2 hydroxide ions dissociate in 1 step. They don't do it stepwise, they do it all at once. So magnesium hydroxide, calcium hydroxide, et cetera, these all go, they both come off. And we know that there's going to be 2 hydroxides produced because there's a subscript of 2 behind the hydroxide in the formula. Sodium hydroxide is a strong base, so if you put it into a solution, no NaOH units will be found. We also have weak bases. Weak bases are like weak acids. They're weak, but they're bases. They can produce OH minus, but they do that by accepting a proton from water, and they cause the water to form hydroxide ions. Generally, organic amines, which have nitrogen in them, are weak bases. So things like ammonia and pyridine, which both have nitrogen in them, are organic amines. They're weak acids. Sodium bicarbonate is also, weak bases. Sodium hydroxide is also a weak base. And in your free time, you can determine the hydroxide concentrations of these basic solutions. Questions?